November 25, 1940, Hatfield Aerodrome, Hertfordshire, England. Geoffrey de Havilland Jr. settled into the cockpit of a bright yellow aircraft that looked more like a furniture factory experiment than a military weapon. His gloved hands gripped the control column of E-0234, a machine the Air Ministry had rejected 3 times, the Royal Air Force called Freeman's Folly, and British aviation officials dismissed as suicide in plywood. Outside, engineers, skeptics and betting men watched the grass runway, wondering if the wooden bomber would even survive takeoff. The prototype weighed 14 to 150 pounds, powered by 2 Rolls-Royce Merlin engines driving constant-speed propellers through a frame constructed almost entirely of plywood, balsa wood and glue. No defensive guns, no armour plating, no metal structure, just wood, fabric, and an engineer's stubborn conviction that speed could replace steel. When de Havilland pushed the throttles forward at 10:45 hours, Britain's most unlikely warplane began its journey from laughingstock to legend, a journey that would make Hermann Göring turn green and yellow with envy, and prove that sometimes genius arrives wrapped in plywood. The conventional wisdom in 1938 was absolute. Modern combat aircraft required metal construction. Bombers needed defensive armament. High-speed aircraft demanded strategic materials. These weren't opinions. They were engineering gospel. The Air Ministry's specification of September 1936 had been crystal clear. Twin-engine bombers must carry 3,000 pounds of bombs, reach 275 miles per hour, and bristle with defensive gun turrets to protect against fighter attack. Every major manufacturer, Vickers, Handley Page, Bristol, followed this blueprint. Heavy bombers like the Wellington and Whitley dominated production. Crews of 6 or 7 men operated complex turret systems. Tons of armour plating protected vital areas. Strategic aluminum and steel flowed into airframe construction at massive scale. The logic seemed unassailable. German fighters like the Messerschmitt Bf 109 were achieving speeds of 350 miles per hour. Without defensive guns, bombers would be sitting ducks. Without metal construction, aircraft couldn't survive combat damage. Without strategic materials, Britain couldn't hope to match German production. The Battle of France had just proven this doctrine correct, or so it seemed. Bristol Blenheim bombers, lightly armed, suffered catastrophic losses, 50% casualties in some squadrons. Luftwaffe fighters slaughtered the vulnerable British bombers. The lesson appeared obvious. More guns, more armour, more metal. Then Sir Geoffrey de Havilland submitted his proposal for the DH-98, a twin-engine bomber built primarily of wood, no defensive armament whatsoever, 2-man crew instead of 7, maximum speed estimated at 400 miles per hour, faster than contemporary fighters. The Air Ministry's response was immediate and unanimous: rejected. September 1938, rejected. March 1939, rejected again. June 1940, after Dunkirk, rejected a 3rd time with instructions to cease all development work. Air Vice Marshal Edgar Ludlow Hewitt, Chief of Bomber Command, stated flatly that an unarmed bomber had no operational value. Lord Beaverbrook, Minister of Aircraft Production, ordered concentration on 5 proven types: Spitfire, Hurricane, Wellington, Whitley, Blenheim, nothing else. No experimental aircraft, no wooden wonders. Production capacity was too precious to waste on pipe dreams. The de Havilland team faced a stark choice: abandon a concept they believed could revolutionise air warfare, or defy direct orders from the highest levels of British aviation authority. They chose defiance and bet Britain's future on a material most nations had abandoned decades earlier. What Air Ministry officials didn't know was that de Havilland possessed knowledge they lacked: experience with wooden construction that bordered on proprietary expertise. In 1934, the company had built the DH-88 Comet Racer, a wooden aircraft that won the 11,000-mile McRobertson Air Race from London to Melbourne. Speed, 232 miles per hour over impossible distances. In 1938, de Havilland flew the DH-91 Albatross airliner, a 22-passenger wooden aircraft cruising at 210 miles per hour, faster than any metal airliner Britain possessed. The company had developed a composite wood construction technique, layers of birch plywood sandwiching balsa wood, bonded with phenolic resin adhesive, strength-to-weight ratio equal to or exceeding aluminum alloys. When Air Marshal Wilfred Freeman received de Havilland's July 1938 proposal, he read something that struck him as prophetic. In times of war, aluminum and steel may not be available in required amounts, while wood likely would be. Freeman recognized strategic brilliance when he saw it. Britain's metal reserves were finite. Tank production consumed vast quantities of steel. Naval construction demanded aluminum for superstructures. Aircraft production competed for the same limited supply. But wood, Britain possessed unlimited forests. Canada supplied spruce and birch. Ecuador provided balsa. The furniture industry, piano factories, cabinet makers, boat builders employed thousands of skilled woodworkers idle, while metal workers strained at capacity. A wooden aircraft could be produced without touching strategic material reserves. Freeman became the lone voice inside the Air Ministry defending de Havilland's folly. When Lord Beaverbrook ordered the project terminated in June 1940, Freeman simply didn't pass along the instruction, a bureaucratic omission that changed aviation history. On July 7, 1940, de Havilland's general manager L.C.L. Murray made Beaverbrook an impossible promise: 50 Mosquitoes by December 1941, 18 months, to design, prototype, test, and produce 50 aircraft of a completely unconventional design using untested materials and unproven construction methods. Beaverbrook, sceptical but desperate for aircraft production that wouldn't drain metal reserves, agreed. On one condition: Mosquito production couldn't interfere with existing work. Tiger Moth trainers, Hurricane repairs, and Merlin engine manufacturing under license took absolute priority. De Havilland was gambling everything on delivering aircraft from a standing start while maintaining full production of existing types. The mathematics were brutal. 20 Mosquitoes by December 1941, with 30 more by March 1942. They had to design production jigs, establish supply chains for wooden components, train workers in composite construction techniques, test structural integrity, prove airworthiness, all while German bombs rained on British factories. The Battle of Britain consumed nearly a third of de Havilland's factory time to air raid warnings and interruptions. In September 1940, Luftwaffe bombers destroyed sections of the Hatfield facility. Equipment losses, worker casualties, production delays, and a wooden bomber prototype sitting in a bomb shelter at Salisbury Hall, a secret facility in the countryside, waiting for engines that might never arrive. The prototype existed because a handful of engineers refused to accept defeat. Chief designer R.E. Bishop led a team working in secret at Salisbury Hall, a moated country house southwest of Hatfield. Winston Churchill's mother had once lived there. Young Winston had fished in the moat, catching a pike whose sleek lines, mounted on a bathroom wall, supposedly influenced designer C.T. Wilkins when shaping the Mosquito's fuselage. The design evolved through hundreds of iterations, every component analyzed for weight reduction without compromising strength. The fuselage was built in two halves joined along a vertical center line. Sandwich construction, outer layers of Canadian birch plywood, middle core of Ecuadorian balsa, inner layers of birch again, total skin thickness, under ½ inch, weight reduction, dramatic, structural integrity, theoretical but unproven. The wing employed the same composite technique, but added complexity. Spruce spars ran the length, carrying the main structural loads. Plywood webs and skinning distributed aerodynamic forces. The entire wing was built as a single unit, mounted above the bomb bay. No metal framework, no rivets, just wood, glue and engineering calculations that had never been stress-tested in combat. Engine nacelles were integrated into the wing leading edge with cooling air intakes recessed to minimize drag. Radiators sat inside the wing, using thermally efficient glycol cooling systems. This arrangement eliminated the external radiators hanging beneath Spitfire wings, radiators that robbed precious speed through parasitic drag. Every design choice prioritized one goal: velocity. The prototype was completed in October 1940, transported by road to Hatfield on November 3rd, and reassembled in a small, blast-proof building. 2 Merlin 21 engines were installed on November 19th. Engine runs began immediately. Geoffrey de Havilland Jr., son of the company founder and chief test pilot since 1937, conducted taxiing trials on November 24th. The control field was unusual, light, responsive, nothing like the heavy bombers he'd tested before. On November 25, 1940, conditions were acceptable for flight, cold but clear, wind manageable. E-0234 sat on the grass runway, painted bright yellow to prevent British anti-aircraft gunners from shooting down their own prototype. De Havilland pushed throttles forward at 10:45 hours. The takeoff was straightforward and easy, according to official records, a phrase that concealed the extraordinary nature of what was happening. A 14-ton, 150-pound aircraft, constructed of materials most nations had abandoned for combat aviation, was accelerating down a grass strip, asking plywood and glue to withstand forces that had broken metal airframes. De Havilland rotated at 110 miles per hour. The Mosquito climbed away from Hatfield, its undercarriage remaining extended until considerable altitude, a precaution in case immediate landing became necessary. The maiden flight lasted 28 minutes. No catastrophic failures, no structural weaknesses, no evidence that wood couldn't do what metal did. A second flight later that day, this time with engine designer John Walker aboard, lasted 30 minutes and reached 220 miles per hour. By December 29, 1940, the prototype was flown to Langley for a demonstration before Lord Beaverbrook and senior government ministers. The performance was stunning. On January 16, 1941, during speed trials, E-0234 raced against a Spitfire Mark II at 22,000 feet. The wooden bomber, larger, heavier, carrying 2 crew members, outpaced the fighter. Speed, 388 miles per hour. The Spitfire managed 369. Air Ministry skeptics fell silent. Freeman's faith was vindicated. On January 1, 1941, an order for 150 Mosquitoes was issued. The paper plane had just become Britain's fastest operational aircraft. Production presented challenges that made design look simple. De Havilland had promised 50 aircraft by December 1941. They delivered 20. The remaining 30 arrived by mid-March 1942. The shortfall wasn't failure. It was the reality of pioneering an entirely new manufacturing methodology, while bombs fell on British factories. Traditional aircraft production relied on metal workers, riveters, and precision machining. Mosquito production required furniture craftsmen, boat builders, and gluing techniques. De Havilland established production lines at multiple locations. Hatfield remained the primary facility. Standard Motors in Coventry contributed fuselage sections. Percival Aircraft built components. dozens of subcontractors, piano factories in High Wycombe, cabinet makers across England, automotive coach builders, produced wooden parts to exacting specifications. Piano makers who'd spent careers crafting soundboards learned to build bomb bays. Boat builders who'd shaped yacht hulls formed fuselage sections. The furniture industry town of High Wycombe, coincidentally Geoffrey de Havilland's birthplace, became a centre of Mosquito component production. Each fuselage half was formed over a mould. Birch plywood layers applied in carefully oriented directions to maximise strength. Balsa core inserted for thickness and rigidity without weight. Final birch layers bonded with phenolic resin adhesive under controlled temperature and pressure. Curing time, critical. Too fast, and resin wouldn't fully bond. Too slow, and production quotas would never be met. The wing presented even greater challenges. Spruce spars had to be precisely engineered. Any flaw would cause catastrophic failure. Plywood web and skin had to bond perfectly to distribute loads. The entire wing was assembled as a single unit measuring 54 feet 2 inches span, then mounted to the fuselage. No metal fasteners in critical stress areas, just glue. Quality control inspectors developed techniques for detecting weak bonds, tap testing with small hammers, visual inspection for delamination, stress testing of sample sections. Any questionable joint was rejected. Lives depended on adhesive bonds holding under combat loads of 8G or more. Production accelerated through 1941 and 1942. June 1941, Air Ministry ordered 1,378 units. By 1942, multiple production lines operated simultaneously. Hatfield alone produced 1 aircraft per line per day at peak output. 4 production lines meant 4 Mosquitoes daily from a single facility. Canada began license production at de Havilland Canada's Downsview facility near Toronto. Australia followed with de Havilland Australia. Total Canadian production, 134 aircraft by 1945. The material logistics were staggering. Each Mosquito required specific wood types sourced globally. Alaskan spruce for spars, strongest strength-to-weight ratio. Canadian birch for plywood, consistent grain, excellent bonding. Ecuadorian balsa for core material, lightest weight, adequate compression strength. English ash for specific structural components. Supply chains stretched across oceans while U-boats hunted convoys. Balsa from Ecuador travelled via ship through U-boat-infested waters. Spruce from Alaska crossed the Pacific, then overland to factories. Birch from Canada faced similar Atlantic crossing risks. Any interruption would halt production. Yet production accelerated. 1942, 378 aircraft ordered. 1943, production hitting stride. 1944, peak output as improved variants entered service. By war's end in 1945, total production reached 7,781 aircraft, 43 different variants serving roles from bomber to fighter to reconnaissance to torpedo bomber to night intruder. The mathematics of the gamble became clear. Britain produced 7,781 Mosquitoes without diverting aluminum or steel from other critical programs. Tanks continued rolling from factories. Naval vessels maintained construction schedules. Metal fighters like Spitfires and Hurricanes never faced material shortages from Mosquito production. The wooden bomber had delivered exactly what de Havilland promised: high-performance aircraft from non-strategic materials. The Mosquito entered operational service in September 1941 when a single aircraft from No. 1 Photographic Reconnaissance Unit flew a mission over occupied France, unarmed, unescorted, relying solely on speed for survival. Mission success complete. The aircraft returned untouched, having photographed strategic targets at speeds German fighters couldn't match. By late 1941, bomber variants began replacing the Blenheim. Mark IV bombers carried 2,000 pounds of bombs internally, 4 500-pound weapons. Speed, 380 miles per hour at 13,000 feet with full combat load. Range, B-1500 miles. Compare this to the Avro Lancaster heavy bomber of the same era. Lancaster, maximum speed 280 miles per hour, crew of 7, bristling with defensive guns. Mosquito, 100 miles per hour faster, crew of 2, 0 defensive armament. The Lancaster carried 4 times the bomb load, 14,000 pounds versus 3,500, but the Mosquito could make the round trip to Berlin and back before the Lancaster returned from the same target. And it could do so twice in the time a Lancaster flew once. September 25, 1942, Operation Oyster. Mosquitoes attacked a Philips radio factory in Eindhoven, Netherlands. Low-level approach at rooftop height, 380 miles per hour across occupied Europe. Bombs released with precision. German defences reacted too slowly. By the time flak guns trained on targets, Mosquitoes were miles away. Mission success with minimal losses proved the concept absolutely. Speed replaced armour. Velocity defeated defensive guns. The bomber had indeed gotten through, not by fighting its way through, but by outrunning everything sent to stop it. January 30th, 1943, Berlin raids. The 10th anniversary of Nazi power. Hermann Göring prepared to address a rally at the Sportpalast, broadcast via Reichsrundfunk Gesellschaft State Radio at 11 a.m. At precisely 11, 3 Mosquitoes from 105 Squadron streaked over Berlin in broad daylight. Flying Officer A. Wickham piloted one. Pilot Officer W. Makin navigated. They climbed to 25,000 feet approaching the capital. Dropped their bombs on the Haus der Rundfunks broadcasting headquarters and turned for home. Göring's speech was delayed 1 hour. The Reichsmarschall, who'd promised no enemy bomber can reach the Ruhr, guaranteeing Germans could call him Meyer if one did, now faced wooden British bombers over Berlin in daylight. That afternoon, 3 more Mosquitoes from 139 Squadron disrupted Joseph Goebbels' speech at another rally. One aircraft, DZ-367, was hit by flak and went down. But 6 British airmen, not 42 in heavy bombers, had humiliated the Luftwaffe on Nazi Germany's most important anniversary. Göring's rage was recorded by stenographers. "I go mad when I look at the Mosquitoes. I'm green and yellow with envy. The Englishman, who has more aluminum than we do, is building a wooden machine, and with a speed which he now increases again." On March 18, 1943, at his Karenhall hunting lodge, Göring summoned German aviation engineers for a 6-hour tirade. He turned to Professor Messerschmitt with barely disguised sarcasm. "It is quite a primitive thing, and there is not much aluminum in it, but it has such a high speed that our aircraft can only attack it from favourable positions." The Luftwaffe, possessing the Messerschmitt Bf-109 and Focke-Wulf FW-190, 2 of the war's finest fighters, couldn't catch a wooden bomber. German night fighter pilots developed Mosquito Schreck, mosquito terror. The fast British bombers began hunting German night fighters that were hunting RAF heavy bombers. Hunter became hunted. By November 1944, Mosquito night fighters had shot down 659 enemy aircraft, 600 over Germany alone. As night fighters, Mosquitoes carried AI Mach-4 and later AI MKX radar, 4 20mm Hispano cannons clustered in the nose, 4 .303-inch Browning machine guns, no synchronization needed, guns fired straight ahead along the aircraft's longitudinal axis, no wing-mounted weapons requiring convergence calculations, just point the nose, fire, and watch German bombers disintegrate. Fighter-bomber variants carried even heavier armament. Mark VI models added 8 60-pound rocket projectiles under the wings. Some carried a 57 cm cannon, a gun capable of destroying any armoured vehicle. The 4,000-pound cookie bomb, a blast bomb designed to destroy buildings, could be carried by specially modified variants. Compare armament density to a Focke-Wulf FW-190, FW-190A8, two 13mm machine guns, 2 or 4 20mm cannons depending on configuration. Wing-mounted, requiring convergence. Synchronized through the propeller arc, reducing rate of fire. Mosquito FB-6, 4 20mm cannons, 4 machine guns, all nose-mounted, all firing forward. Devastating firepower concentrated in a cone directly ahead of the pilot's eyes. As anti-shipping aircraft, Coastal Command Mosquitoes hunted U-boats. Armed with rockets or 57mm cannons, they struck submarine wolf packs in the Bay of Biscay. Operating at low level, they caught U-boats on the surface during charging operations. Rockets or cannon fire, instant kills on surface submarines. The loss rate for Mosquito operations was extraordinary, 0.7%. Compared to heavy bomber loss rates, 2.2% for RAF heavies. Mosquitoes dropped twice as much tonnage of explosives per aircraft lost as heavy bombers. 2-man crews versus 7-man crews meant drastically lower personnel casualties. Over 28,000 operational sorties by war's end. More than 27,000 tons of bombs dropped. Lower loss rate than any other bomber in RAF service. The wooden bomber had revolutionized air warfare through a radical insight. Speed defeats all defenses. German engineers attempted to copy what they couldn't catch. The Focke-Wulf Tar 154 Mosquito, note the German spelling, began development in 1943. Kurt Tank's design team studied captured Mosquito components. The goal was simple: build Germany's version of the wooden wonder. The TR-154 used similar construction. Plywood hull bonded with Tego film phenolic resin adhesive, powered by 2 Junkers UMO 213 engines. Design speed 650 km per hour, matching the Mosquito. Fuji 212 Liechtenstein radar for night operations. Armament 2 20 mm and MG-151 cannons, 2 30 mm and Mk-108 cannons. The prototypes flew well. Initial tests were promising. Then production began, and disaster followed. The Tego film adhesive came from a single factory. Allied bombing destroyed that factory in 1944. Alternative adhesives were tested. They failed catastrophically. TR-154 fuselages delaminated in flight. Wings separated from aircraft. Pilots died. Production stopped completely in September 1944. Only a handful of TR-154s reached operational service with Nachtjagdgeschwader 3. The rest were scrapped or converted to training aircraft. Erhard Milch, who'd personally requested a German Mosquito, watched his wooden fighter program collapse, while British Mosquitoes continued terrorizing German skies. The Heinkel, the Tu-19, became Germany's primary night fighter instead, a metal aircraft. Why did the Mosquito succeed where the TA-154 failed? Manufacturing expertise. De Havilland had decades of composite wood construction experience. The DH-88 Comet of 1934, the DH-91 Albatross of 1938, these weren't experimental aircraft, but proven designs using mature manufacturing techniques. Furniture industry integration gave Britain access to thousands of skilled woodworkers. Quality control protocols were established and refined across hundreds of subcontractors. Germany lacked this foundation. Piano factories in Britain had been building wooden aircraft components since 1941. German piano factories had no such experience or training. The Luftwaffe attempted to copy a manufacturing methodology without possessing the industrial base or expertise to execute it. One captured Luftwaffe intelligence report from March 1943 noted the Mosquito was considerably harder to pick up on radar than metal aircraft. Wooden construction reduced radar cross-section. Not invisible. The spinning propellers were perfect radar reflectors, but significantly more difficult to detect than metal bombers. German radar operators noted they had to vector interceptions closer to get fighters in visual range. By the time German fighters achieved visual contact, Mosquitoes were often accelerating away at speeds the fighters couldn't match in level flight. German fighters could dive on Mosquitoes from superior altitude. But Mosquito pilots quickly learned to exploit their aircraft's superior speed at low altitude. Drop to deck level, open throttles, and disappear. Messerschmitt, Bf-109s and Focke-Wulf FW-190s had higher top speeds in a dive, but in level flight below 15,000 feet, the Mosquito was untouchable. By 1944, Luftwaffe pilots reported that shooting down a Mosquito counted as 2 kills. That's how difficult interception had become. The technical specifications reveal engineering brilliance in every dimension. Wingspan, 54 feet 2 inches. Length, 40 feet 6 inches. Height, 15 feet 3 inches. Empty weight, to 30 to 500 pounds, varying by variant. Maximum takeoff weight, 25-200 pounds. Power plant, 2 Rolls-Royce Merlin engines. Variants use different Merlin marks from Merlin 21 to Merlin 25 to Merlin 113-114. Horsepower ranged from 1,460 to 1,710 depending on engine variant and boost pressure. Maximum speed, over 400 miles per hour. The prototype reached 439 miles per hour in testing, fastest operational aircraft speed recorded at that time. Production variants typically achieved 380 miles per hour at combat weight. Range, 1,500 miles with 4,000-pound bomb load. Extended range variants with drop tanks could reach 3,500 miles. Ceiling, 36,000 feet for high-altitude photo reconnaissance variants. Armament, 4 20mm Hispano cannons, 4 .303-inch Browning machine guns, standard for fighter variants. Bomb load, 2,000 pounds internal for early bombers, increased to 4,000 pounds for later marks. External hardpoints could carry an additional 2,000 pounds on wing racks. Rate of climb, it's at 2,200 feet per minute, unladen. With full bomb load, still over 1,850 feet per minute to 15,000 feet. Wing loading, 40 pounds per square foot. Fuel capacity, 536 gallons internal plus drop tanks. Fuel consumption at cruise, approximately 70 gallons per hour total. Endurance, 8 hours with drop tanks at economical cruise. The engines were the key to everything. Rolls-Royce Merlin V12 liquid-cooled engines. Displacement, 27 litres. Compression ratio, 6.1, supercharged for high-altitude performance. 2-stage, 2-speed supercharging on later variants. These were the same engines powering Spitfires, Hurricanes, and Lancaster bombers. Proven, reliable, powerful. The difference was cooling system integration. Mosquito designers placed radiators inside the wing leading edge. Coolant flowed through ducts integrated into the wing structure. This eliminated external radiators that created parasitic drag. The result, 10 to 15 miles per hour speed increase over externally radiated designs. Oil coolers followed the same integrated design. Everything was recessed, faired, and smoothed for minimum drag. Even the landing gear retracted completely into the engine nacelles. No protruding structures, no external fixtures. Just smooth, continuous surfaces from nose to tail. The control surfaces were fabric covered. Ailerons, elevators, rudder, all fabric on metal frames. This saved weight while providing adequate control authority. Some pilots reported the controls felt stiffer than metal aircraft at high speed. But the response was immediate and precise. The Mosquito could outturn most fighters below 15,000 feet. Not because of superior wing loading, but because of exceptional power-to-weight ratio. and careful aerodynamic design. Stall characteristics were benign. The aircraft gave plenty of warning before stalling. Spin recovery was straightforward. Landing was easier than most twin-engine aircraft. Single-engine performance was adequate if one engine failed. Pilots could maintain altitude on one Merlin if weight was reduced. The structural strength of wooden construction surprised everyone. Combat damage that would cripple metal aircraft merely required wood filler and fabric patches. Bullet holes through plywood fuselages were repaired with cigar box wood. Bomb bay doors made from tea chests served temporarily. In Malta, returning Mosquitos were patched with whatever wood was available, then sent back into combat. The wooden structure absorbed damage better than metal. Metal tears and deforms under stress. Wood splinters and cracks, but maintains overall structural integrity. Numerous accounts document Mosquitos returning from missions with severe battle damage that would have destroyed metal aircraft. One famous incident: a Mosquito FB Mk-6 struck a ship's mast during an anti-shipping attack. The impact should have destroyed the aircraft. The wooden wing absorbed the blow, splintered, but held together. The pilot flew home, landed, and the aircraft was repaired in days. A metal wing would have sheared off completely. By 1944, the Mosquito operated in every theatre of war: Europe, bomber support, precision strikes, reconnaissance; Mediterranean, anti-shipping, tactical bombing; Pacific, reconnaissance, harassment raids. The Royal Australian Air Force operated Mosquitos in the Moluccas and Borneo. Attacking Japanese shipping with rockets and cannons, 6 Canadian squadrons flew Mosquitos in various roles: 400 Squadron, photographic reconnaissance; 406, 409, 410, 418 squadrons, night fighters and intruders; 404 Squadron, anti-shipping and submarine strikes. During the V-1 flying bomb campaign of 1944, Mosquito squadrons shot down 600 V-1 rockets. These were missiles launched from occupied Europe targeting British cities. Cruise speed, 400 miles per hour. Only the fastest Allied fighters could catch them. Spitfires, Hawker Tempests, P-51 Mustangs, Gloucester Meteors, and Mosquitos. 409 Squadron destroyed 10 V-1s. 418 Squadron shot down 82. The wooden bomber, now serving as interceptor, was fast enough to catch unmanned cruise missiles. Special operations became a Mosquito specialty. Operation Jericho, February 18, 1944. Target: Amiens Prison, occupied France. Mission: destroy prison walls to enable escape of French resistance prisoners scheduled for execution. 9 Mosquito FB Mk-6s from 140 Wing attacked at ultra-low altitude, flying 15 meters off the ground in winter conditions. Precision bombing breached outer and inner walls. Hundreds of prisoners escaped. The operation required pinpoint accuracy. Miss by meters and prisoners die, guards survive. Mosquito crews delivered. Copenhagen, March 21, 1945. Target: Gestapo headquarters at Shellhus. Mission: destroy records identifying Danish resistance members. 18 Mosquitoes attacked in 3 waves. Bombs struck the building with devastating accuracy. Top floors destroyed, records incinerated. Gestapo operations in Denmark collapsed. These weren't strategic bombing missions dropping thousands of tons on cities. These were surgical strikes. Specific buildings, specific rooms, minimal collateral damage. Only the Mosquito possessed the speed to penetrate occupied airspace, the accuracy to hit precise targets, and the agility to escape before defences reacted. By war's end in May 1945, Mosquito statistics told the story. 7,181 aircraft built. Britain, Canada, Australia. 43 distinct variants serving every conceivable role. 28,000 operational sorties. 27,000 tons of bombs dropped. 600 plus Luftwaffe aircraft shot down by Mosquito night fighters, 600 V-1 flying bombs destroyed, loss rate, 7%, lowest of any RAF bomber. Operational from September 1941 to final mission, May 24, 1945, hunting German U-boats off Scotland coast. Post-war service continued. Our RAF squadrons operated Mosquitoes through the 1950s until jet aircraft replaced them. The last operational flight occurred in May 1963, No. 3 Civilian Anti-Aircraft Cooperation Unit flying target towing variants. 22 years of continuous service. The Mosquito's legacy transcends statistics. It proved unconventional materials could outperform strategic metals. It demonstrated speed defeats, armor and defensive guns. It showed that small crews in fast aircraft could achieve what large crews in slow aircraft couldn't. Industrial democracy had defeated fascist production methods. British piano factories and furniture makers built 7,781 aircraft without diverting aluminum or steel from other programs. German industry, despite capturing immense resources from occupied territories, couldn't replicate the achievement. Cost analysis revealed staggering efficiency. A Mosquito cost approximately $14,000 to produce in 1943. An Avro Lancaster heavy bomber cost $58,000. 4 Mosquitoes for the price of 1 Lancaster. The Lancaster carried more bombs per sortie, 14,000 pounds versus 4,000. But the Mosquito flew 3 sorties in the time a Lancaster flew 1. Loss rates meant Mosquito crews had significantly higher survival rates. Total cost per ton of bombs delivered, Mosquitoes were 60% more efficient. The American aviation industry studied the Mosquito with interest, but ultimately rejected wooden construction. US manufacturers like Beech and North American submitted evaluation reports citing lack of serviceability, structural weakness, and unsuitable materials. The USAAF report in 1942 called wooden construction an act of desperation. This assessment missed the point entirely. Britain wasn't desperate. Britain was strategic. American industry had unlimited aluminum supplies. Britain did not. American industry prioritized metal production techniques. Britain leveraged existing woodworking expertise. Different strategic circumstances demanded different solutions. The Mosquito was Britain's solution. And it was brilliant. After the war, Geoffrey de Havilland was asked what he considered his greatest achievement. His answer was immediate. The Mosquito, not the jet-powered vampire that followed. Not the Comet jet airliner that pioneered commercial jet travel, the wooden bomber that everyone said was impossible. Of the 7,781 Mosquitoes built, only 30 survive today. 5 remain airworthy as of 2024. The prototype, W4050, rests at the de Havilland Aircraft Museum at Salisbury Hall, the moated house where it was designed and built in secret. Visitors can see the aircraft that changed Geoffrey de Havilland Jr.'s reputation from test pilot to legend, that made Hermann Göring furious with envy, that proved plywood and glue could defeat the finest fighters Germany produced. The final accounting reveals a truth that transcends aviation history. The Mosquito succeeded not because it used wood instead of metal. It succeeded because engineers asked the right question. Not, how do we build a better metal bomber? But, how do we build a bomber that achieves the mission with available resources? The answer was wood. But the principle was strategic thinking. Britain faced aluminum shortages, limited industrial capacity, and desperate need for versatile combat aircraft. The Mosquito addressed every constraint. Non-strategic materials, check. Alternative workforce, furniture makers instead of metal workers, check. Superior performance, faster than fighters, more accurate than heavy bombers, check. Multi-role capability, One airframe serving a dozen missions. Check. Cost efficiency. 4 for the price of one Lancaster. Check. The Luftwaffe never solved this equation. They tried to copy the Mosquito with the TR-154. They failed because they copied the solution, wood, without understanding the problem. Strategic resource allocation. German industry could have built metal fighters and bombers exclusively. That's what they did. British industry built metal fighters, metal heavy bombers, and wooden multi-role aircraft. The mathematical advantage was decisive. Every Mosquito built freed aluminum for a Spitfire. Every Mosquito mission flown saved Lancaster crews from flak and fighters. Every Mosquito precision strike eliminated targets that would have required entire heavy bomber formations. The piano factories that built Mosquitoes contributed as much to Allied victory as the metalworks that built Spitfires. Perhaps more, because they proved that genius finds solutions in unconventional materials when conventional materials are scarce. Hermann Göring's fury was justified. His Luftwaffe possessed excellent engineers, advanced designs, and conquered resources. Yet wooden British bombers dominated German skies. The conclusion was inescapable and humiliating. British ingenuity had defeated German industry. Small teams in piano factories had outproduced massive German aviation conglomerates. Plywood and balsa had bested aluminum and steel. The mathematics of total war are brutal. The Mosquito's production numbers weren't the highest, 7,681 versus 12,731 Avro Lancasters or 2,351 Supermarine Spitfires, but the Mosquito's contribution per aircraft exceeded both. Versatility multiplied effectiveness. A Lancaster was a heavy bomber, excellent at that role, useless for others. A Spitfire was a fighter, superb in air combat, couldn't carry bombs effectively. The Mosquito was bomber, fighter, reconnaissance, night fighter, anti-shipping, pathfinder, intruder, transport. One airframe, a dozen missions, all executed superbly. The 7,181 Mosquitoes built performed the work of 3 times that number of specialized aircraft. That's the genius of the design. Not just speed or wooden construction or defensive armament philosophy, but fundamental versatility achieved through aerodynamic excellence and structural innovation. They laughed at a paper plane built of plywood and glue. They dismissed wooden construction as obsolete, unsuitable, impossible. They rejected it 3 times before grudgingly allowing one prototype. That prototype outran every fighter in the RAF. The production aircraft that followed revolutionized air warfare, humiliated the Luftwaffe, and proved that strategic thinking defeats conventional wisdom. The de Havilland Mosquito wasn't just a wooden wonder. It was proof that engineering brilliance comes from asking better questions, not accepting established answers. When Geoffrey de Havilland Jr. landed E-0234 after that first flight on November 25, 1940, he'd done more than test an unconventional aircraft. He'd validated a philosophy: speed defeats armour, agility defeats guns, and innovation defeats orthodoxy. The wooden bomber they laughed at became the aircraft Hermann Göring envied. The Freeman's Folly became the most versatile combat aircraft of World War II. The paper plane built in piano factories outran the Luftwaffe and helped Britain win the war. 7,781 times, de Havilland proved that genius arrives in unexpected materials. Sometimes the best solution isn't the conventional one. Sometimes plywood defeats steel, furniture makers build weapons, and the impossible becomes inevitable. The Mosquito flew from 1941 to 1963, 22 years of operational service. Longer than the war it was designed to fight, longer than most metal aircraft of its era. The wooden wonder outlasted its critics, outlived its doubters, and proved that when engineering excellence meets strategic vision, materials matter less than imagination. They laughed at a paper plane. Then it outran the Luftwaffe, rewrote the rules of air warfare, and earned its place among history's greatest aircraft, not despite being made of wood, because of it, 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 because of it.